We're trapped, and most people don't even realize it. There's an invisible barrier surrounding our solar system, not made of walls or force fields, but something far more absolute: distance itself. Even at the fastest speed the universe allows, the nearest star is still 4 years away, and we can't even reach a fraction of that speed. Today, I'm going to show you why the cosmos might have locked us in a cage we can never escape. And here is a question for you. Where in the universe would you go if you could travel at 1 light year per second? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let's start with something that might blow your mind. Right now, the fastest human-made object ever created is hurtling through space at mind-boggling velocity. It's called the Parker Solar Probe, and it reached speeds of around 430,000 miles per hour. That's roughly 192 kilometers per second. To put that in perspective, at that speed, you could travel from New York to Tokyo in less than a minute. Sounds incredibly fast, doesn't it? But here's where things get humbling. At that incredible velocity, the fastest we've ever achieved, it would still take this probe about 6,500 years to reach Proxima Centauri, the nearest star to our Sun. 6,500 years. That's longer than all of recorded human civilization. The pyramids of Egypt were built only about 4,500 years ago. When the Parker Solar Probe would finally arrive at Proxima Centauri, everyone you know, everyone they know, and hundreds of generations beyond them would be long gone. This is the first unsettling truth about interstellar travel. Space is unimaginably, almost incomprehensibly vast. Our galaxy, the Milky Way, stretches about 100,000 light-years across. A light-year is the distance light travels in 1 year, moving at roughly 670 million miles per hour, or 186,000 miles per second. Even at that insane speed, it would take light 100,000 years to cross our galaxy. Our galaxy is just one among an estimated 200 billion galaxies in the observable universe. When you look up at the stars tonight, you're not just seeing distant suns, you're seeing the past. The light from Proxima Centauri that reaches your eyes tonight left that star over 4 years ago. The light from Betelgeuse, that bright reddish star in the constellation Orion, left that star around 540 years ago, before Shakespeare was even born. Some of the galaxies we observe through our telescopes are so far away that their light has been traveling toward us for billions of years. We're literally looking back in time, seeing these galaxies as they were when the universe was young, when Earth didn't even exist yet. This brings us to Einstein and his theory of relativity, which fundamentally changed how we understand space, time, and the possibility of interstellar travel. Before Einstein, scientists thought you could theoretically just keep accelerating faster and faster forever. But Einstein discovered something profound. Nothing with mass can ever reach the speed of light. As you approach light speed, strange things happen. Your mass effectively increases, requiring more and more energy to accelerate further. Time itself slows down for you relative to everyone else. Space contracts in the direction you're moving. And here's the absolute cosmic speed limit. Light travels at exactly 299,792,458 meters per second in a vacuum. That's it. That's the universal speed limit, and nothing can break it. Not you, not me, not the most advanced spaceship we could ever dream of building. Now, before you feel completely hopeless about ever exploring the stars, remember that science is full of surprises. Humans once thought flying was impossible. We once believed Earth was the center of the universe. We thought atoms were the smallest possible things until we discovered quarks and leptons. The universe has a habit of revealing loopholes, clever workarounds, and possibilities we never imagined. Here's where things get fascinating. Even though we can't break the cosmic speed limit, scientists and engineers around the world are working on technologies that could potentially get us closer to light speed than ever before. These aren't just wild fantasies, these are real projects backed by real science with real funding from serious institutions and brilliant minds. One of the most ambitious projects in recent years was called Breakthrough Starshot. Announced back in 2016 by physicist Stephen Hawking and funded with $100 million by entrepreneur Yuri Milner, this initiative aimed to prove that interstellar travel was actually possible within a human lifetime. The concept was revolutionary. Instead of building massive spaceships that would take thousands of years to reach another star, why not build incredibly tiny spacecraft, so small they weigh less than a gram, and push them using powerful lasers? Before we go further, if you're finding this fascinating, hit that subscribe button and give this video a thumbs up. It really helps this channel grow and lets me know you want more deep dives into the mysteries of our cosmos. Plus, you'll be joining a community of curious minds exploring the biggest questions in the universe together. The idea behind Breakthrough Starshot was beautifully elegant. These miniature spacecraft, called nanocrafts, would be attached to ultra-thin light sails, essentially mirrors just atoms thick, but meters wide. A massive array of lasers on Earth would fire powerful beams at these sails, and the pressure from billions of photons hitting the sail would accelerate the craft to about 20% of light speed. At that velocity, one of these tiny probes could reach Alpha Centauri, our nearest stellar neighbor, which is actually a system of 3 stars, in just about 20 years. 20 years. Think about that. A mission launched today could send back pictures and data from another star system while the scientists who launched it are still alive to see the results. That's incredible. That's revolutionary. That represents a fundamental shift in how humanity could explore the cosmos. But, and this is a significant but, Breakthrough Starshot faced enormous technical challenges. How do you build a spacecraft weighing less than a paperclip that can survive temperatures of thousands of degrees as it's accelerated by laser fire? How do you communicate with something so small across trillions of miles? How do you aim it accurately enough that it doesn't miss its target after traveling for 20 years through space? And perhaps most importantly, how do you slow it down when it gets there? Or is this just a high-speed flyby where you get maybe hours or minutes to observe before you zoom past at 56 million miles per hour? According to recent reports, the Breakthrough Starshot program has been paused. Despite the ambitious goals and significant funding, the engineering challenges proved more daunting than initially anticipated. Some estimates suggest that only about $4.5 million of the promised $100 million was actually spent on the project. Work is now underway to transfer some of the research to other programs. Does this mean the dream is dead? Not at all. It means we're learning. Every failed attempt, every technical challenge identified, every calculation that doesn't work out teaches us something valuable. Science progresses through both breakthroughs and setbacks. The Wright brothers' first flights lasted only seconds, but they proved powered flight was possible. Breakthrough Starshot, even in its incomplete state, proved that serious scientists and engineers believe interstellar travel is theoretically achievable, not just science fiction. So if laser-powered nanocrafts face such enormous hurdles, what other options do we have? Let's explore the different propulsion technologies scientists have proposed for interstellar travel. And trust me, some of these ideas sound like they're straight out of science fiction, but they're rooted in real physics. First, let's talk about conventional chemical rockets, the kind we've been using since the space age began. These work by burning fuel and shooting hot gas out the back, which pushes the rocket forward. It's the same principle as a balloon flying around a room when you let the air out. Chemical rockets got us to the moon. They've sent probes to every planet in our solar system, and they're incredibly reliable. But here's the problem. They're painfully slow for interstellar distances. The Voyager 1 spacecraft, launched back in 1977, is currently the most distant human-made object from Earth. It's traveling at about 38,000 miles per hour relative to the Sun. That sounds fast until you realize it would take Voyager over 73,000 years to reach Proxima Centauri, if it were even headed in that direction, which it isn't. Chemical rockets simply can't carry enough fuel to accelerate to the speeds we need for interstellar travel. The faster you want to go, the more fuel you need, but more fuel means more weight, which means you need even more fuel to push that weight, and you end up in what engineers call the tyranny of the rocket equation. This fundamental limitation led scientists to dream bigger. What if instead of chemical reactions we used nuclear reactions? After all, nuclear energy releases millions of times more energy per kilogram than chemical fuel. This thinking gave birth to concepts like nuclear pulse propulsion, first seriously studied in a project called Orion back in the 1950s and 60s. The Orion concept was audacious even by today's standards. The idea was to literally drop nuclear bombs behind a spacecraft and ride the shockwaves. Small nuclear devices would be ejected from the back of the ship, detonated at a safe distance, and a massive shock absorber plate would catch the blast, converting the explosion's energy into forward thrust. Calculations suggested this could potentially reach a few percent of light speed, meaning a journey to Alpha Centauri might take somewhere between 80 to 150 years. Still a multi-generational voyage, but vastly better than chemical rockets. However, there's an obvious problem here. Detonating thousands of nuclear bombs in space carries enormous political, environmental, and practical challenges. The Partial Nuclear Test Ban Treaty of 1963 essentially killed the Orion project by prohibiting nuclear explosions in space, but the physics behind it? Solid. The concept proved that if we're willing to harness extreme energy sources, we can achieve much higher speeds than conventional rockets. Another nuclear approach that's slightly less explosive is nuclear electric or nuclear thermal propulsion. These systems use nuclear reactors to either superheat propellant to extremely high temperatures or generate electricity to power ion drives. Ion drives work by accelerating charged particles to very high speeds using electromagnetic fields. They provide much less thrust than chemical rockets. We're talking about the force equivalent to holding a few coins in your hand, but they can run continuously for years, gradually building up to impressive velocities. NASA's Dawn spacecraft used ion propulsion to visit the asteroids Vesta and Ceres between 2011 and 2018. Over its mission, the ion drive changed the spacecraft's velocity by more than 25,000 miles per hour. Imagine if we scaled that up, used a nuclear reactor for power instead of solar panels, and let it run for decades. We could potentially reach several percent of light speed, making an interstellar journey possible within a few centuries rather than millennia. But even nuclear propulsion has limits. The amount of fuel you'd need to carry for a decades-long acceleration phase is still enormous. This is where more exotic propulsion concepts enter the picture, ideas that sound impossible but are actually permitted by the laws of physics as we currently understand them. One of the most fascinating is antimatter propulsion. Here's where the universe gets really strange. For every particle in the universe, electrons, protons, neutrons, there exists an antimatter counterpart with opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy, converting 100% of their mass into energy according to Einstein's famous equation, E equals mc squared. No other reaction in nature is that efficient. Nuclear fusion, the process that powers our sun, converts less than 1% of mass into energy. Chemical reactions, a tiny fraction of a percent. If we could somehow collect or create antimatter, store it safely and use it as fuel, we could theoretically achieve velocities up to a significant fraction of light speed. Some designs suggest that an antimatter rocket could reach perhaps 50 to 80% of light speed, reducing travel time to Proxima Centauri to just 5 or 6 years. That's a journey within a single human lifetime. You could launch a mission as a young scientist and see the results before you retire. But, and this is a massive but, we currently produce antimatter in particle accelerators at a rate of only a few nanograms per year, and it costs roughly $62 trillion per gram. To fuel an antimatter rocket for an interstellar mission, you'd need kilograms of the stuff. We're talking about an energy and economic investment that makes the entire global GDP look like pocket change. Plus, storing antimatter without letting it touch any regular matter and annihilate is an engineering nightmare that we've barely begun to solve. Still, the fact that antimatter propulsion is physically possible, not just theoretical fantasy, tells us something important about the universe. The laws of physics don't absolutely forbid interstellar travel. They make it extraordinarily difficult and expensive, yes, but not impossible. Now here's where I want to recommend another video on this channel that dives deeper into this very topic. If you're fascinated by why even light speed presents limitations we haven't fully discussed yet, check out my video called Why the Fastest Thing in the Universe Still Isn't Fast Enough. It explores the deeper implications of relativistic speeds and why even traveling at light speed wouldn't solve all our problems. You'll find it linked in the description and in the cards above. Let's consider another mind-bending concept: solar sails and their more advanced cousin, laser sails, which we touched on with breakthrough Starshot. The basic principle is beautifully simple. Light has momentum. Even though photons have no mass, they carry momentum. And when they bounce off a reflective surface, they transfer that momentum, creating a tiny push. It's the same principle behind why comet tails always point away from the sun. The sun's light is literally pushing the dust and gas away. A solar sail is essentially a giant mirror in space, sometimes kilometers across, but only micrometers thick. As sunlight strikes the sail, the spacecraft very slowly accelerates. The acceleration is tiny, but it's continuous and requires no fuel. You're basically surfing on starlight. The Japanese space agency JAXA successfully demonstrated this technology with their Icaros spacecraft back in 2010, and NASA's Advanced Composite Solar Sail System recently tested new materials for more efficient sails. For interstellar missions, though, solar sails face a fundamental problem. The farther you get from the sun, the weaker the sunlight becomes, following an inverse square law. Double the distance, and the light intensity drops to 1/4. At interstellar distances, sunlight becomes so weak it's essentially useless for propulsion. This is why concepts like breakthrough Starshot proposed using powerful Earth-based lasers instead. You could theoretically keep beaming energy to the spacecraft for weeks or months during its acceleration phase, pushing it to a significant fraction of light speed before it gets too far away. Recent research published in 2025 explored advanced photonic light sails using metamaterials and inverse design techniques. These aren't just simple mirrors anymore. Scientists are designing nano-engineered surfaces that can manipulate light in sophisticated ways, potentially solving stability problems that have plagued light sail concepts. When you're being pushed by a laser beam across trillions of miles, even a tiny wobble or misalignment gets amplified enormously. These new photonic materials could help keep the spacecraft on course, but even with these advances, fundamental questions remain. You're essentially turning your spacecraft into a giant kite being blown by a laser wind. How do you steer? How do you slow down when you arrive? Remember, there's no laser at Alpha Centauri to help you brake. You'd be screaming past your destination at tens of thousands of miles per second, maybe getting a few hours to snap pictures and take measurements before disappearing into the void beyond. Some scientists have proposed using the destination star's own light to slow down, essentially flipping the sail around and using starlight as a brake. The math suggests this might work, but it would require the sail to survive not just the acceleration phase and decades of interstellar travel, but also remain functional enough to execute a deceleration maneuver with split-second timing. We're talking about a piece of material thinner than plastic wrap that needs to remain perfectly functional for 20 years while traveling through the harsh radiation environment of interstellar space. Here's something that might surprise you. We're actually living in a golden age of propulsion research. More scientists are working on interstellar travel concepts now than at any previous point in human history. Organizations like the Initiative for Interstellar Studies, the Tau Zero Foundation, and university research groups around the world are seriously studying these problems. They're not just daydreaming, they're doing the math, running the simulations, testing materials, and slowly, incrementally, pushing the boundaries of what's possible. The universe isn't holding back its secrets out of malice. It's simply operating according to fundamental laws that we're still learning to work with rather than against. Every time we think we've hit an insurmountable wall, human ingenuity finds a crack, a loophole, or a completely different approach we hadn't considered. Now let's venture into territory that sounds even more like science fiction, but is actually grounded in serious theoretical physics. What if, instead of trying to go faster, we changed the nature of space itself? What if we could bend, fold, or shortcut through space-time? This is where concepts like warp drives and wormholes enter the conversation. And believe it or not, these aren't just fantasy, they're solutions to Einstein's equations of general relativity. General relativity tells us that space and time aren't fixed, rigid things. They're flexible, dynamic, woven together into what physicists call space-time. Massive objects like stars and planets actually bend space-time around them. And this bending is what we experience as gravity. When you're standing on Earth, you're not being pulled down by some mysterious force. You're actually following the curved geometry of space-time created by Earth's mass. It's like a bowling ball sitting on a stretched rubber sheet, creating a dip that smaller objects roll toward. If massive objects can bend space-time, could we artificially manipulate space-time to enable faster-than-light travel? In 1994, physicist Miguel Alcubierre published a paper describing what's now called the Alcubierre drive, or warp drive. His mathematical solution to Einstein's equations showed that you could theoretically create a bubble of space-time around a spacecraft. In front of the ship, you'd compress space, making distances shorter. Behind the ship, you'd expand space. The ship itself wouldn't be moving through space at all. Space itself would be moving around the ship. Think of it like standing on a moving walkway at an airport. You're not walking faster, but the floor beneath you is moving, carrying you forward. An Alcubierre drive would be similar, except instead of a moving floor, you'd be surfing on a wave of compressed and expanded space-time. Inside the bubble, time flows normally, you experience no acceleration forces, and technically you're not violating the cosmic speed limit because you're not actually moving through space. Space is moving around you. Sounds perfect, right? Well, here come the problems, and they're substantial. First, the amount of energy required to create and maintain such a space-time distortion is absolutely staggering. Early calculations suggested you'd need negative energy, yes, energy with a negative value, equivalent to the total mass energy of Jupiter. Later refinements reduced this to maybe the mass energy of a small planet or a large asteroid, which sounds like progress until you realize we're still talking about converting something the size of a small planet into pure energy and somehow controlling it precisely enough to warp space-time. Second, this requires something called exotic matter with negative mass or negative energy density. As far as we know, such matter doesn't exist in any substantial quantity in nature. The Casimir effect in quantum mechanics produces tiny amounts of negative energy at microscopic scales, but scaling this up to spacecraft-size bubbles is a challenge that makes every other engineering problem we've discussed look trivial by comparison. Third, and this is particularly interesting, recent mathematical analyses suggest that an Alcubierre drive might create intense radiation at the front of the bubble. When you eventually turn off the drive and stop at your destination, all this accumulated radiation would be released in a catastrophic burst that could potentially sterilize whatever planet or star system you just arrived at. Imagine traveling across the galaxy only to accidentally destroy your destination with a gamma-ray burst. That's not exactly the friendly first contact scenario we've been hoping for. Despite these monumental challenges, physicists haven't given up on the concept. In 2021, physicist Eric Lentz proposed a modified warp drive design that might not require negative energy. Instead, it would use configurations of positive energy sources to create the necessary space-time distortion. The energy requirements are still enormous. We're talking about harnessing energy equivalent to hundreds of times the mass of Jupiter, but at least it doesn't require exotic matter that might not exist. Progress comes in small steps, even in theoretical physics. Another mind-bending possibility is wormholes, also called Einstein-Rosen bridges. These are theoretical tunnels through space-time that could connect two distant points in the universe. Imagine folding a piece of paper so two distant dots touch, then poking a hole through both layers. Instead of traveling across the surface of the paper, you could take a shortcut through the hole. That's essentially what a wormhole would do with space-time. The equations of general relativity permit wormholes to exist, but there's a catch, there's always a catch. A naturally occurring wormhole would be incredibly unstable, collapsing almost instantly unless it's held open by, you guessed it, exotic matter with negative energy density. You'd need to thread the wormhole with this exotic matter to keep it stable enough for anything to pass through. And even if you could do that, there's the small problem of actually creating or finding a wormhole in the first place. Some theoretical models suggest that microscopic wormholes might constantly pop into and out of existence at the quantum scale, part of what's called quantum foam. If true, the challenge would be to capture one of these quantum wormholes, stabilize it, and somehow inflate it to macroscopic size without it collapsing. We're talking about technology so far beyond our current capabilities that it's like explaining nuclear reactors to someone living in the Stone Age. But here's what's fascinating. None of these concepts violate the known laws of physics. They're extraordinarily difficult. They require technology we can barely imagine. They need resources on a scale we've never attempted, but they're not impossible according to our current understanding of the universe. There's a crucial difference between incredibly hard and fundamentally impossible. Let's bring this back to reality for a moment. While we're exploring warp drives and wormholes in theory, what could we actually accomplish with technology we have now, or could realistically develop in the next few decades? This is where concepts like generation ships and sleeper ships come into play. A generation ship is exactly what it sounds like, a massive spacecraft large enough to sustain a complete human society for the centuries-long journey to another star. The people who launch wouldn't be the ones who arrive. Their children wouldn't arrive. Their grandchildren wouldn't arrive. Depending on the destination and propulsion system, it might take 5, 10, or even 20 generations before the descendants of the original crew finally reach their new home. Think about the psychological and sociological challenges here. You're asking people to voluntarily board a ship, knowing they'll never see their destination, that their entire lives will be spent in an enclosed environment, all for the benefit of descendants they'll never meet. What kind of culture would develop on such a ship? How would you maintain social cohesion and purpose across multiple generations? What happens if people born on the ship decide they don't want to continue the mission? Science fiction has explored these questions extensively, but they're not just fictional concerns, they're genuine problems that would need solutions before we could attempt such a mission. Some researchers study isolated communities like research stations in Antarctica or submarines to better understand how humans cope with long-term confinement in closed environments. Others look at historical examples of long ocean voyages or isolated settlements to identify patterns and potential problems. The engineering challenges are equally daunting. A generation ship would need to be entirely self-sufficient for centuries. You'd need to recycle absolutely everything: water, air, waste, with near-perfect efficiency. You'd need to grow all your food in controlled environments, maintain genetic diversity in both humans and crops, repair everything that breaks using only materials already on board, and do all of this with perfect reliability for hundreds of years. Consider this: the longest continuous human presence in space is currently the International Space Station, which has been continuously occupied since November 2nd, 2000. That's a little over 25 years, impressive, but it relies on constant resupply missions from Earth. Everything from food to spare parts to new crew members arrives regularly on cargo ships. A generation ship would have none of that support. Once you launch, you're on your own. An alternative concept is suspended animation or cryogenic sleep. Instead of having generations of people living and dying on the journey, what if we could simply put the crew to sleep and wake them up when they arrive? This solves many of the generation ship problems. You'd need much less living space, far fewer resources, and the original crew would actually see their destination. But here's the reality check. We currently have no proven technology for safely putting humans into suspended animation for extended periods. We can freeze certain tissues and cells, and there have been some promising experiments with inducing hibernation-like states in animals that don't normally hibernate. Some surgical patients have been cooled to dramatically slow their metabolism during complex operations. But freezing and reviving an entire human being without causing catastrophic damage? That's still science fiction. The fundamental problem is ice crystal formation. When water freezes, it expands and forms crystals that can rupture cell membranes. Your cells are mostly water, so freezing a person causes massive damage at the cellular level. Some organisms, like wood frogs and certain insects, survive freezing by producing natural antifreeze compounds and controlling where ice forms in their bodies. We've tried to replicate these strategies with cryoprotectant chemicals, but scaling this up from individual cells or small tissues to an entire human body remains an unsolved challenge. There's another approach called vitrification, where tissues are cooled so rapidly that water forms an amorphous glass-like state instead of crystalline ice. This works better than slow freezing, but it requires extremely rapid cooling and warming, and even then we've only succeeded with relatively small samples, cooling and warming an entire human body quickly enough to vitrify all tissues uniformly. Nobody's figured out how to do that yet. Some companies offer cryonic preservation services, freezing recently deceased individuals with the hope that future technology will be able to revive and cure them. But it's crucial to understand that this is an extremely speculative bet on future capabilities. No human has ever been successfully revived from cryonic preservation, and we don't actually know if the process preserves enough of the brain structure to maintain memories and personality. So if freezing humans is problematic, what about just slowing down metabolism without freezing? This is called torpor or hibernation, and it's something various animals do naturally. Bears hibernate through winter, drastically reducing their metabolic rate and living off stored body fat for months. Ground squirrels can lower their body temperature to near freezing while remaining alive in a state of suspended animation. If we could trigger something similar in humans, even reducing metabolism by 50 or 75%, the resource requirements for a long interstellar voyage would drop dramatically. Research in this area is actually progressing. NASA has funded studies into therapeutic hypothermia and torpor-inducing techniques, partly for long-duration Mars missions, but also with an eye toward more distant destinations. Some experiments have successfully induced hibernation-like states in animals that don't normally hibernate, including rats and pigs, by targeting specific neurons in the hypothalamus region of the brain. These animals successfully entered torpor, their body temperature and metabolism dropped significantly, and they woke up afterward apparently unharmed. Scaling this to humans involves considerable unknowns. Human physiology evolved in very different environments than hibernating animals. We don't have the same protective mechanisms against muscle atrophy, bone density loss, or neural degradation during prolonged inactivity. Astronauts on the International Space Station exercise for hours every day just to counteract the muscle and bone loss from a few months in microgravity. Imagine lying motionless for years or decades. What would that do to your body even if we could keep you alive? Still, the fact that research is happening, that serious scientists are working on these problems with actual funding and publishing peer-reviewed results, tells us something important. These challenges, while substantial, aren't considered insurmountable by the scientific community. They're engineering and medical problems, not violations of fundamental physics. Let's shift perspective for a moment and consider a radically different approach to interstellar exploration. What if we don't send humans at all? What if we don't even send traditional robots? What if we send information? Here's a thought experiment that some futurists and philosophers take seriously. If we could map the complete structure of a human brain, every neuron, every synapse, every connection, and create a perfect digital simulation of that brain, would that simulation be conscious? Would it be you in any meaningful sense? This concept is called mind uploading or whole brain emulation, and while it sounds like pure science fiction, there are researchers seriously investigating whether it's theoretically possible. The human brain contains roughly 86 billion neurons, each connected to thousands of others through trillions of synapses. Mapping all of this is called creating a connectome. Scientists have successfully mapped the connectomy of a tiny worm called C. elegans, which has only 302 neurons. That project took over a decade. Scaling up to a human brain represents a challenge that's many orders of magnitude more difficult, but it's not necessarily impossible given enough time and technological advancement. If mind uploading ever becomes possible, interstellar travel suddenly looks very different. You wouldn't need life support, food, water, or protection from radiation. You could transmit a human consciousness as information, as a data stream, at the speed of light to a receiver at the destination star system. The journey to Proxima Centauri would take just over 4 years, the light travel time, rather than centuries or millennia. Of course, this raises profound philosophical questions. Is a digital copy of your consciousness really you, or is it a separate being that merely thinks it's you? If the original, you remains on Earth while a copy travels to the stars. Which one is the real you? These aren't just abstract philosophy, they're questions that would have serious ethical and practical implications if this technology ever becomes real. There's also a more modest version of this concept that doesn't require uploading human minds at all. Instead of sending humans, we could send sophisticated artificial intelligence. Current AI systems are becoming increasingly capable of autonomous decision-making, pattern recognition, and even creative problem-solving. Imagine sending an AI-controlled probe to another star system, one that can make its own decisions, conduct experiments, analyze results, and transmit findings back to Earth without waiting years for instructions. This approach has major advantages. AI doesn't need life support, doesn't age, doesn't get bored during a centuries-long voyage, and can be backed up digitally. If something goes wrong, you haven't lost human lives. Multiple probes could be sent to different destinations, each carrying sophisticated AI capable of conducting real science autonomously. When they arrive, they could even potentially build more equipment using resources found at the destination, creating what's called a self-replicating probe. The concept of self-replicating probes was seriously analyzed by mathematician John von Neumann back in the 1940s. A von Neumann probe would arrive at a star system, find an asteroid or moon with useful raw materials, build copies of itself using those resources and send those copies to other star systems. Each copy would do the same thing. Given enough time, a single self-replicating probe could theoretically explore the entire galaxy through exponential reproduction. Before you worry about being overrun by replicating robots, there are obvious concerns here. Uncontrolled replication could theoretically consume vast resources, creating what's sometimes called the grey goo scenario. Any civilization developing this technology would need extremely robust safeguards to prevent runaway replication. But with appropriate controls, self-replicating probes represent a way that even a relatively modest initial investment could lead to comprehensive exploration of countless star systems. Let's talk about communication, because even if we solve the propulsion problem, staying in contact with an interstellar mission presents its own unique challenges. Radio waves and laser communications travel at light speed, which is as fast as information can possibly travel according to physics. This means there's an unavoidable time delay based on distance. If we send a message to a probe at Proxima Centauri, it takes over 4 years for the signal to arrive. If the probe responds immediately, we won't receive that response for another 4 years. That's more than 8 years for a round-trip conversation. Ask a question on Monday, get an answer 8 years later. This makes real-time control impossible. Any spacecraft traveling to another star must be largely autonomous, capable of making decisions without waiting for instructions from Earth. The farther the spacecraft travels, the more difficult communication becomes. Signal strength decreases with the square of distance, so a signal from Proxima Centauri arrives at Earth with only 1/16 the strength of a signal from half that distance. To maintain communication over interstellar distances, you need either extremely powerful transmitters, extremely sensitive receivers, or both. NASA's Deep Space Network, which communicates with distant probes like Voyager, uses massive dish antennas up to 70 meters in diameter. Even with this equipment, the signal from Voyager 1, which is only about 15 billion miles away, still within our solar system, arrives with a power of only about 1/10,000th of a billionth of a watt. That's roughly the same amount of power as a digital watch battery, but spread across the entire surface of Earth. Receiving it requires some of the most sensitive equipment ever built. Now imagine a probe at Proxima Centauri, which is about 1,700 times farther away than Voyager. The signal would arrive at about 1/3 millionth the strength, or roughly 3 million times weaker. Detecting that would require either much larger antennas, much more powerful transmitters on the spacecraft, or revolutionary advances in receiver technology. Some proposals suggest using the Sun itself as a gravitational lens to amplify signals from interstellar space, but that's technology we're only beginning to understand how to develop. There's another subtle but important challenge, the Doppler shift. When something is moving toward or away from you, the frequency of light or radio waves changes. You've experienced this with sound. An ambulance siren sounds higher pitched when approaching and lower pitched when moving away. The same thing happens with light and radio waves. A spacecraft traveling at even a few percent of light speed would have significant Doppler shift, meaning we'd need to constantly adjust our receiving frequency to stay tuned to the probe's transmission. At relativistic speeds, meaning a significant fraction of light speed, the Doppler shift becomes extreme. Light from something approaching you at 80% of light speed would be blue shifted by a factor of 3, meaning visible light becomes ultraviolet or even X-rays. Light from something moving away at that speed would be red shifted so far into the infrared that you'd need special detectors just to see it. Our receiving equipment would need to account for this across the entire journey as the spacecraft accelerates and eventually cruises at constant velocity. Despite all these challenges, we're actually getting better at both sending and receiving very weak signals across vast distances. Modern error correction codes can extract meaningful information from signals that are almost completely buried in background noise. Quantum communication technologies being developed today might eventually allow even more efficient data transmission. Every year, our ability to communicate across the solar system improves slightly, and these incremental advances add up over decades. Here's something that might surprise you. We've actually already sent messages intended for potential extraterrestrial civilizations, and we've been inadvertently broadcasting our presence for over a century. Every radio and television transmission that's ever been sent has radiated out into space at the speed of light. Right now, there's a bubble of human-generated radio signals expanding outward from Earth at light speed, currently about 115 light-years in radius. Any civilization with sufficiently sensitive receivers within that bubble could potentially detect us. More deliberately, we've sent specific messages into space. The Arecibo message was transmitted in 1974 toward the globular cluster M13, about 25,000 light-years away. Voyager 1 and 2 carry golden records with sounds and images from Earth. Pioneer 10 and 11 carry plaques showing our location in the galaxy. These are essentially cosmic messages in bottles, more symbolic than practical, but they represent humanity's deep desire to reach out beyond our cosmic neighborhood. Now let's address something that often gets overlooked in discussions about interstellar travel: the environment of interstellar space itself. We tend to think of space as empty, and compared to Earth's atmosphere, it certainly is. But empty is relative, and even the tiny amount of stuff floating between stars creates serious problems at high velocities. Interstellar space isn't a perfect vacuum. It contains roughly 1 atom per cubic centimeter on average. That's incredibly sparse compared to Earth's atmosphere, which contains about 2.5 times 10 to the 19th power molecules per cubic centimeter. But here's the critical issue. When you're traveling at a significant fraction of light speed, even individual atoms become deadly projectiles. Imagine driving down a highway in the rain. At normal speeds, raindrops splatter harmlessly on your windshield. But if you could somehow drive at a significant percentage of light speed, those same gentle raindrops would hit with the force of bullets. The faster you go, the more kinetic energy each impact carries, following the equation for kinetic energy: 1/2 mass times velocity squared. Double your speed and the impact energy quadruples. At 10% light speed, a single hydrogen atom, the lightest element in the universe, hits with the energy of a particle accelerator beam. At 20% light speed, which is what breakthrough Starshot was aiming for, every collision with an interstellar hydrogen atom releases energy equivalent to about 200 electron volts. That might not sound like much, but when you're hitting millions or billions of these atoms every second across the surface of your spacecraft, the cumulative effect is like flying through a constant barrage of radiation. This cosmic sandblasting would gradually erode any exposed surface, potentially damaging electronics, degrading materials, and creating secondary radiation as atoms in your ship's structure are knocked loose by impacts. For a tiny probe weighing less than a gram, like the nanocrafts proposed for breakthrough Starshot, even a collision with something slightly larger, say a dust grain a millimeter across, would be catastrophic. At 20% light speed, that dust grain would hit, with the kinetic energy of about 5 kilograms of TNT exploding. Your entire spacecraft would be vaporized instantly. The probability of such a collision over a journey of 4 light-years is actually not negligible, which is why mission designers would need to either accept a certain failure rate and send many probes, or develop some kind of shielding or detection system. Some proposals suggest using electromagnetic fields to deflect charged particles before they hit the spacecraft. Others propose a sacrificial shield in front, essentially a barrier designed to take the impacts and gradually erode, protecting the critical systems behind it. Still others suggest using powerful lasers to vaporize incoming particles before collision. Each approach has drawbacks. Magnetic shields require significant power and might not work on neutral particles. Physical shields add mass, reducing acceleration. Laser defense systems add complexity and power requirements. There's another hazard lurking in interstellar space: radiation. Far from the protective magnetic field of Earth or any star, cosmic rays, high-energy particles accelerated by supernova explosions, black holes, and other violent cosmic events constantly bombard anything in space. Some of these particles carry truly staggering amounts of energy. The most energetic cosmic ray ever detected, nicknamed the "Oh my God" particle, and observed in 1991, carried about 50 joules of energy, roughly equivalent to a baseball thrown at 60 miles per hour, but concentrated in a single subatomic particle. For human crews on interstellar voyages, cosmic radiation poses a serious long-term health risk. Unlike the relatively gentle radiation environment near Earth, where our planet's magnetic field deflects most cosmic rays, interstellar space offers no protection. Extended exposure increases cancer risk, can damage the central nervous system, potentially causes cataracts, and might accelerate aging. Any crewed interstellar vessel would need substantial radiation shielding, which adds mass, which requires more propulsion energy, bringing us back to the tyranny of the rocket equation. Interestingly, water is an excellent radiation shield because hydrogen atoms are effective at absorbing high-energy particles. Some spacecraft designs propose surrounding the crew compartment with water storage tanks, serving dual purposes as both necessary life support and radiation protection. Materials rich in hydrogen, like certain plastics, also work well. The challenge is carrying enough shielding mass without making your spacecraft too heavy to accelerate efficiently. Let's talk about navigation, because hitting your target after traveling for decades through interstellar space is far more difficult than you might imagine. When NASA sends a probe to Mars or Jupiter, they can continuously track its position, calculate its trajectory, and send course corrections. The spacecraft might make dozens of small adjustments during the journey, ensuring it arrives precisely where intended. An interstellar spacecraft faces unique challenges. First, the vast distances mean that even small errors in initial trajectory compound dramatically. If your aim is off by just 1 degree when you launch, you'll miss Alpha Centauri by about 740 billion miles, nearly 100 times the distance from Earth to the Sun. That's not a near miss, that's not even in the right neighborhood. Second, stars move. Alpha Centauri isn't sitting still in space, it's moving relative to our Sun at about 22 kilometers per second. Over the 20 years it might take a fast probe to get there, Alpha Centauri will have moved about 14 billion kilometers, roughly the distance from the Sun to beyond Neptune's orbit. Your navigation system must account for where the star will be when you arrive, not where it is when you launch. Third, gravitational influences from every massive object between here and there will subtly alter your trajectory. The Sun's gravity, other stars' gravity, even the collective gravity of interstellar gas clouds can nudge your path over time. Calculating all these influences precisely enough to hit a target 4 light-years away is extraordinarily complex. For a probe that can't make course corrections, like a laser-pushed light sail with no onboard propulsion, you get one chance to aim correctly. If you miss, there are no second tries. This is why mission designers talk about sending fleets of probes rather than single spacecraft. With multiple probes spread slightly apart, you increase the odds that at least some will pass close enough to the target to accomplish the mission objectives. For spacecraft with onboard propulsion capable of making course corrections, you face a different challenge: navigation sensors and computing power. How do you know where you are when you're between star systems with no familiar landmarks? On Earth, we use GPS satellites, but there's no interstellar GPS network. Early ocean navigators used stars and the Sun to determine position, but in deep space, the perspective changes so slowly that using stars for navigation during the journey requires extremely precise measurements. One promising approach is pulsar navigation. Pulsars are rapidly rotating neutron stars that emit regular pulses of radio waves, acting like cosmic lighthouses. Each pulsar has a unique rotation rate, creating a distinctive signal pattern. By observing multiple pulsars and measuring the exact timing of their pulses, a spacecraft can theoretically triangulate its position anywhere in the galaxy to within a few kilometers. NASA tested a pulsar navigation system called Sextant on the International Space Station between 2017 and 2018, successfully demonstrating that the concept works in near-Earth space. Scaling this up for true interstellar navigation is challenging but appears feasible. Here's a question that might not have occurred to you. What powers an interstellar spacecraft during its journey? If you're near the Sun, solar panels work great. This is how most satellites and Mars rovers get their electricity, but solar panel effectiveness drops with distance. At Jupiter's orbit, solar panels receive only 4%, as much sunlight as at Earth. At Pluto's distance, it's less than 1,000th. In the darkness between stars, solar panels are essentially useless. Nuclear power becomes necessary for deep space and interstellar missions. The Voyager spacecraft use radioisotope thermoelectric generators, or RTGs, which convert heat from decaying plutonium-238 into electricity. These devices have no moving parts, require no maintenance, and continue working for decades. Voyager 1's RTG has been functioning for nearly 48 years now, though its power output gradually decreases as the plutonium decays. By the time Voyager reaches distances comparable to the nearest stars, tens of thousands of years from now, its RTG will have long since gone cold. For missions designed to reach other stars within human timescales, power requirements are much higher. You need electricity to run computers, scientific instruments, communication systems, and potentially life support for crew. A fission reactor, similar to those in nuclear submarines but adapted for space, could provide substantial power for decades. Some advanced designs propose fusion reactors, which could theoretically run for centuries if supplied with enough fuel, but practical fusion reactors remain elusive even for Earth-based applications, let alone spacecraft. There's a fascinating concept called a Bussard ramjet that attempts to solve both the fuel and propulsion challenges simultaneously. Proposed by physicist Robert Bussard in 1960, this hypothetical spacecraft would use enormous magnetic fields, perhaps thousands of kilometers wide, to scoop up hydrogen atoms from interstellar space as it travels. These collected atoms would then be fused in an onboard reactor, providing both power and propulsion. It's an elegant idea. Your spacecraft collects its own fuel as it goes, like a cosmic jet engine breathing in the interstellar medium. Unfortunately, detailed analysis revealed serious problems with the Bussard ramjet. The density of interstellar hydrogen is so low that the energy required to maintain the massive magnetic fields and operate the fusion reactor might exceed the energy gained from the collected fuel, especially at lower speeds. Some calculations suggest a Bussard ramjet might actually slow down rather than speed up. Various modifications have been proposed to address these issues, but as of now, the concept remains theoretical and problematic. Let's explore one of the strangest aspects of traveling at relativistic speeds: the bizarre effects that Einstein's special relativity predicts will happen to time itself. This isn't science fiction or speculation. These effects have been measured, tested, and confirmed countless times in particle accelerators and with atomic clocks on fast-moving aircraft. They're real, they're strange, and they fundamentally change what interstellar travel would feel like. Einstein discovered that time doesn't flow at the same rate for everyone. Time passes more slowly for objects moving at high speeds relative to stationary observers. This phenomenon is called time dilation, and at everyday speeds, the effect is so tiny you'd never notice it. But as you approach the speed of light, time dilation becomes dramatic. Here's what this means for interstellar travel. Imagine a spacecraft accelerates to 80% of light speed and travels to a star 20 light-years away. From Earth's perspective, the journey takes about 25 years, 20 light-years divided by 0.8 light speed, plus some time for acceleration and deceleration. But for the crew aboard the spacecraft, time passes more slowly. Due to time dilation, they experience only about 15 years passing during the same journey. They age 15 years while everyone on Earth ages 25 years. The faster you go, the more extreme this becomes. At 90% of light speed, a crew experiences time passing at only about 44% the normal rate. At 99% of light speed, it's about 14%. At 99.99% of light speed, only about 2% of normal time passes for the crew. A journey that takes 100 years from Earth's perspective might feel like only 2 years to the travelers. This creates a profound and unsettling consequence. You could theoretically travel to distant stars and return within your own lifetime, but everyone you knew on Earth would be long dead. Your children might have grown old and passed away. Civilizations might have risen and fallen. You'd be a time traveler moving into Earth's future without any way to return to your own present. Science fiction often portrays this as the twin paradox. One twin boards a spacecraft, accelerates to near light speed, travels to a distant star, and returns. The traveling twin might age only 10 years during the journey, while the twin who remained on Earth has aged 50 or 60 years. When they reunite, the traveling twin is now decades younger than their sibling. This isn't a thought experiment, it would actually happen. The laws of physics not only allow it, they require it. Some people wonder whether the effect is symmetrical. Doesn't the Earth-based twin also appear to be moving from the spacecraft's perspective? The answer involves acceleration. The traveling twin must accelerate to reach high speed, decelerate at the destination, accelerate again to return, and decelerate when arriving back at Earth. These acceleration phases break the symmetry, and it's the traveler who ages more slowly, not the person who stays home. This has been confirmed experimentally with atomic clocks on aircraft and satellites. The moving clock consistently runs slower, exactly as Einstein predicted. There's another relativistic effect called length contraction. At high speeds, distances appear compressed in the direction of motion. From the spacecraft's perspective, the distance to the destination star actually becomes shorter. At 80% of light speed, a distance of 20 light-years compresses to about 12 light-years from the traveler's viewpoint. At 99.99% of light speed, that 20 light-years shrinks to less than 3/10 of a light-year. In a sense, relativistic speeds don't just make time pass differently, they literally change the geometry of space itself from the traveler's perspective. Combined, time dilation and length contraction mean that from the crew's perspective, interstellar journeys become much shorter than you'd calculate using simple distance divided by speed. This is why some physicists point out that even with current physics, traveling to distant parts of the galaxy is theoretically possible within a human lifetime if you can reach high enough speeds. The catch, of course, is achieving those speeds, which brings us back to all the propulsion challenges we've discussed. Now let's address the elephant in the room. Why would we even attempt interstellar travel? What's driving this desire to reach other stars? The answer connects to some of humanity's deepest questions and most profound motivations. First, there's survival. Earth won't last forever. In about 5 billion years, our sun will expand into a red giant, eventually engulfing Earth's orbit. Long before that, increasing solar luminosity will make Earth uninhabitable, potentially within 1 billion years. On shorter timescales, we face risks from asteroid impacts, supervolcano eruptions, climate change, nuclear war, pandemics, or technologies we haven't even invented yet. Having human civilization confined to a single planet means one catastrophic event could end our entire story. Establishing humanity on multiple worlds, ideally in multiple star systems, dramatically improves our species' long-term survival odds. Stephen Hawking argued passionately for this perspective. He believed humanity must become a multi-planet and eventually multi-stellar species to ensure our long-term survival. It's not just about escaping specific threats, it's about building resilience into the very structure of human civilization. A civilization spread across multiple star systems can't be wiped out by any single catastrophe. Second, there's knowledge. The universe is vast, ancient, and full of mysteries we've barely begun to explore. Every star is unique. Every planetary system has its own story. The conditions that gave rise to life on Earth might exist around countless other stars, and studying those worlds could answer fundamental questions. How common is life in the universe? Does life inevitably arise given the right conditions? Are there other forms of intelligence out there? What can other worlds teach us about planetary formation, atmospheric chemistry, geology, and the origins of life itself? We've discovered over 5,000 confirmed exoplanets orbiting other stars since the first detection in the early 1990s. We know that planets are common, that many stars have them, and that some orbit in the habitable zone where liquid water could exist on the surface. But all our knowledge comes from incredibly distant observations, analyzing starlight filtered through atmospheres, measuring tiny wobbles in stellar motion, detecting minuscule dips in brightness as planets cross in front of their stars. These techniques are brilliant and have revolutionized our understanding of planetary systems, but they give us only crude information. To really understand these worlds, to analyze their atmospheric chemistry in detail, to search for biosignatures indicating life, to study their geology and weather patterns, to determine if any harbor actual living organisms, we need to go there. No telescope, no matter how powerful, can match this scientific value of an actual probe studying another world up close. Think about how much we've learned from rovers on Mars compared to what we could see from Earth-based telescopes. Now imagine that leap in understanding applied to worlds around other stars. Third, there's something deeply human about exploration itself. Throughout our history, humans have wondered what lies beyond the next hill, across the next ocean, above the clouds. We're a curious species. We explore not just for practical reasons, but because the unknown calls to us. The same impulse that drove ancient Polynesians to navigate vast stretches of Pacific Ocean, that inspired European explorers to sail beyond the known world, that pushed mountaineers to climb the highest peaks, that same drive compels us to look at the stars and wonder what's out there. This isn't frivolous. Curiosity-driven exploration has consistently led to unexpected benefits. The Apollo program's goal was to reach the moon, but the technologies developed along the way, miniaturized electronics, advanced materials, medical devices, water purification systems, transformed life on Earth. GPS satellites were developed for military navigation, but now underpin everything from smartphone maps to precision agriculture to global shipping. You can't predict what useful discoveries will emerge from pushing the boundaries of what's possible. There's also a perspective that comes from contemplating our place in the cosmos. When you look up at the night sky and realize that each point of light is an entire sun, potentially with its own family of planets, some perhaps harboring life, it changes you. It makes our differences seem smaller, our shared humanity more obvious. Every person who's traveled to space and looked back at Earth describes a similar experience. Seeing our planet as a fragile blue marble floating in the darkness with no visible borders, all of humanity sharing this one precious world. Interstellar travel takes this perspective even further. If we could stand on a planet orbiting another star and look back toward our sun, just another point of light among billions, we'd see ourselves as we truly are, one species on one small world, orbiting one ordinary star in one galaxy among trillions. That perspective is humbling and inspiring at the same time. Carl Sagan captured this beautifully when describing the pale blue dot photograph taken by Voyager 1 from the edge of the solar system in 1990. Earth appears as a tiny pixel, a pale blue dot suspended in a sunbeam. Sagan wrote about how every human who ever lived their entire life on that mote of dust, how all our triumphs and tragedies, wars and romances played out on that barely visible speck. He argued that contemplating this should inspire both humility and a sense of responsibility to preserve and cherish that pale blue dot, because as far as we know, it's the only home we have. Interstellar exploration extends that vision. It says that while Earth is precious and irreplaceable, our story doesn't have to be confined to this one world. We can carry Earth's legacy, life, intelligence, curiosity, art, science, all the remarkable things that evolution produced here, out into the galaxy. We can become not just a planetary species, but a stellar one, spreading life and consciousness among the stars. There's another motivation that's often overlooked in discussions about interstellar travel, the question of whether we're alone in the universe. This isn't just idle curiosity, it's one of the most profound questions humans have ever asked. The search for extraterrestrial intelligence, or SETI, has been listening for signals from space for over 60 years now, and so far we've heard nothing but cosmic silence. This silence is puzzling and has given rise to what's called the Fermi paradox, named after physicist Enrico Fermi. During a lunch conversation in 1950, Fermi asked a simple but profound question: where is everybody? Given that our galaxy is about 13.6 billion years old, and the technological civilizations could theoretically spread across the galaxy in just a few million years, even with slow, sublight speed travel, why haven't we detected any evidence of other civilizations? Why haven't they visited us? Why aren't they obvious? There are dozens of proposed solutions to the Fermi paradox, and exploring them reveals just how uncertain our assumptions about life and intelligence really are. Maybe life is far rarer than we think. Maybe intelligence almost never evolves. Maybe technological civilizations inevitably destroy themselves before achieving interstellar travel. Maybe they're out there but have no interest in communicating with or visiting primitive civilizations like ours. Maybe the distances between stars really are too vast, and interstellar travel is simply impractical, even for advanced civilizations. Or maybe, and this is a sobering thought, we're actually among the first. The universe is still relatively young. The first generation of stars contained almost no heavy elements: carbon, oxygen, iron, all the elements necessary for planets and life were forged in those stars and scattered by supernovas. It took billions of years for enough heavy elements to accumulate for rocky planets like Earth to form. Maybe we're part of the first wave of intelligence in the universe, the pioneers who will eventually fill a galaxy that's currently empty of conscious observers. If that's true, then interstellar travel becomes even more significant. It means we have a responsibility not just to ourselves, but potentially to the universe itself. We might be carrying the torch of consciousness into a dark galaxy, and what we do in the next few centuries could shape the cosmic future for billions of years to come. Let's talk about realistic timelines. When could humanity actually attempt interstellar travel? Not science fiction scenarios, but actual, achievable missions given plausible technological development. Most experts break this down into several phases, each with different goals and capabilities. Phase 1, which we could call the precursor missions, involves sending probes to the outer solar system and eventually to the interstellar medium just beyond our sun's influence. We've actually already achieved this. Voyager 1 crossed into interstellar space in 2012, and Voyager 2 followed in 2018. These probes aren't headed toward any specific star, and they're moving so slowly they'll take tens of thousands of years to pass anywhere near another stellar system, but they've given us our first taste of the space between stars. Future precursor missions might be more ambitious. NASA has studied concepts for an interstellar probe that would specifically target the interstellar medium, traveling much faster than Voyager using advanced propulsion systems, possibly reaching 150 to 200 astronomical units from the Sun, about 4 to 5 times Voyager's current distance, within 15 to 20 years. This probe would study the boundary region where our Sun's influence gives way to interstellar space, measuring magnetic fields, particle densities, and cosmic ray intensity. It would lay groundwork for understanding the environment any true interstellar mission would face. Phase 2 involves missions that actually target other star systems, but are still essentially one-way scientific missions without any intention of landing, establishing colonies, or returning. These would be fast flyby missions, concepts like the Breakthrough Starshot initiative we discussed earlier. Launch within the next 30 to 50 years seems plausible if the technical challenges can be solved and funding secured. These missions would teach us immense amounts about engineering, navigating, communicating across interstellar distances, and studying other stellar systems up close. If we're being realistic, the first interstellar probe that humans send will probably be small, fast, autonomous, and designed for a flyby rather than an extended mission. It might carry sophisticated cameras, spectrometers, particle detectors, and magnetometers, but it won't slow down or orbit. It'll scream through the target system at tremendous velocity, frantically gathering data during a brief window of a few hours or days, then continue into the darkness beyond while transmitting its findings back to Earth. Phase 3 would be missions designed to actually slow down and enter orbit around another star or its planets. This is vastly more challenging than a flyby because you need propulsion, not just for acceleration, but also for deceleration. Remember, there's no air in space to brake against, and you can't rely on the destination star's laser beam to help you slow down. You either need to carry fuel for deceleration, which dramatically increases the mass you must accelerate in the first place, or you need some other clever solution, like using the destination star's magnetic field or light pressure from the sail in reverse. Realistically, orbital missions to other stars are probably a century or more away with current technology trends. But a century isn't that long in the grand scheme of history. A person born today might live to see the first proposals for such missions being seriously planned, even if the actual launch happens after their lifetime. Phase 4 would be missions carrying actual colonists intending to establish permanent human presence around other stars. This is where we're talking about generation ships, suspended animation, or perhaps mind uploading if that ever becomes possible. These missions represent such enormous challenges, technical, biological, social, psychological, that most experts place them at least several centuries in the future, possibly much longer. But here's something interesting. The timeline could compress dramatically if we make unexpected breakthroughs. History is full of technologies that seemed impossibly distant suddenly becoming real within decades. In 1900, powered flight seemed like a fantasy. 69 years later, humans walked on the moon. In 1950, computers were room-sized machines owned only by governments and major corporations. 70 years later, billions of people carry devices in their pockets with computational power that would have seemed miraculous to those early computer pioneers. If someone invents a practical fusion drive or discovers a way to manipulate space-time that doesn't require planet-mass amounts of exotic matter or solves the suspended animation challenge, the entire timeline for interstellar exploration could suddenly collapse from centuries to decades. We genuinely don't know what breakthrough might happen tomorrow that changes everything. There's also the possibility of what futurists call a technological singularity, a point where artificial intelligence becomes so advanced that it begins improving itself recursively, leading to incomprehensibly rapid technological advancement. If that happens, And if we successfully align superintelligent AI with human values and goals, it might solve problems we currently think are impossible. Of course, this assumes we handle AI development wisely, which is far from guaranteed. Let's talk about the economics of interstellar travel, because ultimately, someone has to pay for this. The International Space Station cost roughly $150 billion spread across multiple nations and decades. The Apollo program cost about $190 billion in today's currency. These are enormous investments, but they're within the capacity of wealthy nations or international collaborations. Interstellar missions would almost certainly cost far more. A true generation ship capable of supporting thousands of people for centuries would likely require an investment measured in trillions of dollars. Even relatively modest missions like laser-pushed nanocrafts would need massive infrastructure. Think kilometer-scale laser arrays with power requirements comparable to small countries. Who would fund such projects? National governments, like those that funded Apollo and the space station, are possibilities, but political horizons rarely extend beyond a few election cycles. Projects lasting decades or centuries require stability and commitment that's difficult to maintain through changing administrations and shifting public priorities. Private funding is another possibility. Wealthy entrepreneurs like Yuri Milner have already invested in interstellar research through breakthrough initiatives. Others like Elon Musk with SpaceX and Jeff Bezos with Blue Origin have shown that private citizens can fund major space initiatives. As wealth concentrates and as space-related industries potentially become profitable, private funding for ambitious projects might increase. International collaboration represents another path. Just as multiple nations cooperate on the International Space Station, on large telescopes like the Extremely Large Telescope being built in Chile, and on particle physics facilities like CERN, interstellar missions might eventually be international efforts. When the goal is benefiting all of humanity rather than any single nation, cooperation becomes easier to justify. There's also an economic argument that investment in space technology drives economic growth through spin-off technologies and industries. The space industry currently generates hundreds of billions of dollars annually in satellite communications, Earth observation, GPS services, and space tourism. As space industry grows, it creates wealth that could potentially fund more ambitious projects. Mining asteroids for rare metals, establishing solar power stations in space, or developing other space-based industries could eventually create enough economic value to fund interstellar exploration as a side project of a mature, spacefaring civilization. Let's consider what finding life on other worlds would mean for humanity. We're not talking about necessarily finding intelligent aliens, though that would be profound. Even discovering simple microbial life on Mars, or in the oceans beneath the ice of Jupiter's moon Europa, or Saturn's moon Enceladus, would fundamentally change our understanding of life's place in the universe. If life arose independently on two worlds in the same solar system, it would strongly suggest that life emerges readily given the right conditions. Our galaxy contains somewhere between 100 billion and 400 billion stars, and we now know most of them have planets. If life is common, then even if only a tiny fraction of life-bearing worlds develop intelligence, the galaxy could be teeming with civilizations. Finding even single-celled organisms on another world in our solar system would revolutionize the Drake equation, the formula scientists use to estimate the number of communicating civilizations in our galaxy. But what if we don't find life anywhere else in our solar system? What if Mars is sterile, Europa's ocean is lifeless, and Enceladus contains only chemistry without biology? That would also tell us something important. Perhaps Earth really is special. Perhaps life is far rarer than we hoped, requiring such specific conditions that only one world in billions meets the criteria. In that case, interstellar travel becomes even more significant because we might need to search thousands of star systems before finding another world where life emerged. This brings us to the concept of terraforming, deliberately modifying other worlds to make them habitable for Earth life. If we develop the capability for interstellar travel but find that most worlds are barren rock, ice, or gas, terraforming might be how we establish humanity among the stars. Mars is often discussed as a potential terraforming candidate. It once had liquid water on its surface, it has polar ice caps, and while its atmosphere is currently thin and mostly carbon dioxide, theoretical models suggest it might be possible to thicken the atmosphere and warm the planet over centuries or millennia using various techniques. Interstellar terraforming would be even more ambitious. Imagine arriving at a star system after a journey of decades or centuries and finding a rocky planet in the habitable zone, but with an atmosphere that's toxic to humans, maybe too much carbon dioxide or methane or sulfur compounds. With sufficiently advanced technology, you might engineer microorganisms designed to gradually transform that atmosphere over thousands of years. Similar to how photosynthetic bacteria transformed Earth's early atmosphere from oxygen-poor to oxygen-rich about 2.4 billion years ago in what's called the Great Oxidation Event. This raises ethical questions that science fiction has explored, but that we might actually need to answer. Do we have the right to deliberately modify other worlds, potentially destroying any native ecosystems that might exist, even simple ones? If we find a planet with microbial life but no complex organisms, is it ethically acceptable to terraform it for human colonization, essentially committing xenocide, the killing of alien life? These questions have no easy answers, but they're worth thinking about now before we develop the capability to face them in practice. There's a concept in planetary protection policy called forward contamination, the possibility that Earth life carried on our spacecraft might contaminate other worlds. We already deal with this for Mars missions. Spacecraft sent to Mars are carefully sterilized to avoid bringing Earth microbes that might survive there and confuse our search for Martian life, or worse, actually colonize Mars and outcompete any native life that might exist. For interstellar missions, especially crewed ones, preventing forward contamination becomes nearly impossible. A generation ship carrying thousands of humans would inevitably carry vast quantities of Earth microbes in our bodies, on our skin, in our gut. We're walking ecosystems, and anywhere humans go, Earth's biosphere follows. Some argue this is actually acceptable or even desirable. If life is rare, then spreading Earth's biosphere to lifeless worlds could be seen as a cosmic good, taking this precious thing that arose on Earth and ensuring it survives and flourishes on multiple worlds. Others argue we should proceed with extreme caution, preserving any native life we find and only colonizing truly lifeless worlds. Still others suggest a middle path. Carefully study any world before making irreversible changes, and only terraform if we're certain we're not destroying existing ecosystems. Let's shift gears and talk about the psychological aspects of interstellar travel. What would it actually be like to be part of an interstellar mission? If you're on a generation ship, you're born, live your entire life, and die inside a relatively small enclosed environment, never seeing Earth, never breathing open air, never feeling rain or seeing an ocean. Your children are born there. Your grandchildren are born there. Generations pass. Some will reach the destination. Most won't. Psychologists and sociologists who study isolated communities have identified various challenges. Cabin fever and interpersonal conflicts arise even in well-trained groups. The overwinter crews at Antarctic research stations, typically 15 to 50 people spending months in isolation, experience mood changes, sleep disruptions, and occasional conflicts despite careful screening and training. A generation ship would face similar challenges multiplied across decades or centuries, and involving thousands of people who weren't screened astronauts but ordinary individuals born into the mission. How do you maintain social cohesion across generations? How do you preserve knowledge and technical skills needed to maintain the ship? What happens if social problems arise? What if part of the population wants to turn back, or wants to stop at a different destination, or develops religious or ideological differences that threaten the mission? On Earth, conflicting groups can separate and move to different regions. On a generation ship, you're stuck together with limited space and no exit option. Some researchers study closed ecological systems as models for generation ships. Biosphere 2, an experimental facility in Arizona, attempted to create a completely closed ecosystem with 8 people sealed inside for 2 years, starting in 1991. The experiment encountered numerous problems. Oxygen levels dropped, carbon dioxide built up, most vertebrate species died, and interpersonal conflicts developed among the crew. While the experiment provided valuable data about closed systems, it also highlighted how difficult maintaining a truly self-sufficient environment actually is. For a generation ship, you'd need robust recycling systems for water, air, and nutrients with virtually no loss over decades. You'd need sufficient genetic diversity in both humans and food crops to avoid inbreeding problems. You'd need redundancy in all critical systems, plus the ability to manufacture spare parts from raw materials. Because resupply missions from Earth wouldn't be possible, you'd need stable social structures, effective governance, education systems, meaningful work, entertainment, and ways for people to find purpose in a mission that won't be completed in their lifetime. Yet despite these challenges, human history suggests we might be capable of such journeys. Polynesian voyagers crossed vast stretches of Pacific Ocean in outrigger canoes, traveling for weeks without seeing land, navigating by stars, waves, and birds, settling islands thousands of miles from their origin points. These weren't single voyages, but multi-generational migrations spanning centuries, with knowledge passed down through oral traditions and apprenticeship. If humans could accomplish that with Neolithic technology, perhaps we could handle generation ships with advanced life support and scientific knowledge. Religious pilgrimages provide another historical parallel. Groups throughout history have endured hardship traveling toward promised lands, whether the Israelites wandering 40 years in the desert according to biblical accounts, Mormon pioneers crossing the American plains in the 1840s, or various other migrations driven by faith and hope for a better future. People can endure tremendous difficulty if they believe the destination is worth the journey and if the community shares common purpose and values. There's also evidence that humans adapt remarkably well to unusual environments given time. People live comfortably in deserts, Arctic regions, high mountains, on boats at sea, environments that seem harsh but become normal when you grow up in them. Children born on a generation ship wouldn't miss Earth because they never knew it. Their normal would be the ship, just as someone born in the Arctic doesn't miss tropical beaches because that's not their reference point. What about communication with Earth? As the ship travels farther from home, the time delay grows. At 1 light-year distance, a message takes 1 year to arrive, and any response takes another year. At 2 light years, it's a 4-year round trip. Eventually, real-time conversation becomes impossible, replaced by carefully crafted messages sent across the years. You might send a message to Earth in your 20s and receive a response when you're elderly, from people who were children or not yet born when you sent your original message. This temporal isolation would be profound. News from Earth would arrive years out of date. Cultural references, politics, current events, everything would be historical by the time you heard about it. Meanwhile, your society on the ship would develop its own culture, customs, and identity. Language might even begin to diverge as isolated populations develop their own dialects, slang, and expressions. By the time the ship reaches its destination, the people aboard might feel more connection to each other than to the increasingly distant and alien culture of Earth. Some science fiction explores the idea that a generation ship might actually decide not to complete its mission. After several generations, with Earth a distant memory and the ship having become home, would anyone actually want to settle a new planet? You'd have to land, learn to live under gravity again after generations in space, deal with unpredictable weather, native microorganisms if any exist, and all the challenges of establishing settlements on a new world. Some might prefer to keep traveling, turning the ship itself into a permanent home, a civilization in a bottle exploring the galaxy without ever settling down. Now let's talk about what we might find when we actually reach another star system. Our understanding of exoplanets, planets orbiting other stars, has exploded in recent decades. Before 1995, we hadn't confirmed a single planet beyond our solar system. Today, as I mentioned earlier, we've confirmed over 5,000, with thousands more candidates awaiting verification. Each discovery teaches us something new about how planetary systems form and evolve. We've found hot Jupiters, massive gas giants, orbiting incredibly close to their stars, completing an orbit in just days, with surface temperatures reaching thousands of degrees. These challenged our theories because giant planets shouldn't form that close to stars. They likely formed farther out and migrated inward. We've found super-Earths, rocky planets more massive than Earth but smaller than Neptune, a planetary type that doesn't exist in our solar system but appears common elsewhere. We've discovered systems with planets in bizarre orbits, multiple star systems where planets orbit 2 or even 3 suns, rogue planets drifting through space without any star at all. The variety is staggering and humbling. Our solar system, which we once assumed was typical, now appears to be just one arrangement among countless possibilities. This suggests that when we finally send probes to other stars, we should expect surprises. The universe is more creative than our imaginations. One particular category of exoplanets fascinates astronomers and astrobiologists, potentially habitable worlds. These are rocky planets orbiting in their star's habitable zone, not too hot, not too cold, but at a distance where liquid water could exist on the surface. Water is essential for all life we know, making it a logical starting point in the search for alien biology. Proxima Centauri, our nearest stellar neighbor, has at least 2 confirmed planets. Proxima Centauri b, discovered in 2016, orbits in the habitable zone with a minimum mass about 30% larger than Earth. It completes an orbit in just 11 days because it's very close to its star, but since Proxima Centauri is a small, cool red dwarf, that close orbit still places the planet in the habitable zone. Could liquid water exist there? Possibly. Could life have arisen? We have no way to know without going there or building telescopes powerful enough to study its atmosphere in detail. However, red dwarf stars like Proxima Centauri present challenges for life. They're prone to violent flares, sudden eruptions of radiation and charged particles that could strip away a planet's atmosphere over time. Proxima Centauri b is tidally locked, meaning one side always faces the star, while the other faces eternal darkness, just like the Moon always shows the same face to Earth. This creates extreme temperature differences that might make habitability difficult, though atmospheric circulation might distribute heat if the planet has a thick atmosphere. The TRAPPIST-1 system, about 40 light-years away, offers another intriguing possibility. Discovered in 2017, this system contains 7 Earth-sized planets orbiting a cool red dwarf star with 3 or possibly 4 planets in the habitable zone. It's like a miniature solar system packed into a space smaller than Mercury's orbit around our Sun. Multiple potentially habitable worlds in a single system increase the odds that at least one might harbor life. Imagine sending a probe to TRAPPIST-1. The journey at 10% light speed would take 400 years, at 20% light speed, 200 years. Still multi-generational timescales, but within the realm where careful planning and stable institutions might maintain continuity. When the probe arrives, it could study all 7 worlds, potentially finding different stages of planetary evolution different atmospheric compositions, maybe even comparing a lifeless world to one where biology emerged. The scientific return from such a mission would be incalculable. There's also Kepler 452b, nicknamed Earth 2.0 by some enthusiasts. Discovered by the Kepler Space Telescope in 2015, this planet orbits in the habitable zone of a Sun-like star, roughly 1,400 light-years away. It's about 60% larger than Earth and receives roughly the same amount of light from its star as Earth receives from the Sun. Its orbital period is 385 days, remarkably similar to Earth's year. If it has a rocky composition and an atmosphere, conditions might be strikingly Earth-like. Of course, 1,400 light-years is vastly farther than our nearest neighbors. Even at 10% light speed, the journey would take 14,000 years. At 50% light speed, pushing the absolute limits of any plausible near-term technology, it would still take 2,800 years. This is squarely in the realm of multi-generational missions or highly speculative technologies like suspended animation or mind uploading. Yet the possibility that a world so similar to Earth might exist out there fires the imagination. The James Webb Space Telescope, launched on December 25, 2021, is revolutionizing our ability to study exoplanet atmospheres. By analyzing starlight filtered through a planet's atmosphere as it transits in front of its star, Webb can detect chemical signatures of various molecules: water vapor, carbon dioxide, methane, oxygen, and potentially biosignatures that might indicate life. In 2023, Webb detected carbon dioxide in the atmosphere of WASP-39b, a hot gas giant, demonstrating the technique works. Applying this to smaller, rocky worlds in habitable zones is more challenging, but potentially achievable. What biosignatures might we look for? On Earth, oxygen makes up 21% of the atmosphere, almost entirely produced by photosynthetic life. Without constant replenishment by living organisms, oxygen would react with rocks and disappear within a few million years. Finding significant oxygen in another planet's atmosphere, especially combined with methane, which oxygen normally reacts with, could suggest biological processes. Other potential biosignatures include certain combinations of gases that wouldn't naturally occur together in a lifeless atmosphere, or complex organic molecules that require biological synthesis. However, we need to be cautious. Not all oxygen is biological. Photodissociation, where ultraviolet light breaks apart water molecules, can produce oxygen without life. Some geological processes can generate methane. False positives are possible, which is why astrobiologists emphasize the importance of looking for multiple biosignatures together, patterns that can't be explained by non-biological chemistry alone. There's also the fascinating possibility of finding technosignatures, evidence of technology rather than just biology. Radio signals, laser pulses, atmospheric pollution from industrial processes, artificial lighting on a planet's night side, megastructures like Dyson spheres that capture a star's energy. These would indicate not just life, but technological civilization. SETI researchers have been searching for such signals for decades without success, but absence of evidence isn't evidence of absence. Maybe we haven't looked long enough, or in the right places, or at the right frequencies. Or maybe technological civilizations are simply rare or short-lived. If we did detect a technosignature from another star system, it would immediately become humanity's most important discovery and likely the highest priority target for interstellar exploration. The thought of sending a probe to a star system we know contains intelligent life is both thrilling and sobering. What would we say? What would we hope to learn? How would we ensure our probe doesn't pose a threat or cause harm? These questions transition from philosophy to practical policy the moment we detect another civilization. Let's consider the possibility that we find ruins rather than living civilizations. A planet with artificial structures, clearly technological in origin, but no active signals, no living inhabitants. This would suggest that civilizations can arise, achieve spacefaring capability, or at least planet-wide technology, and then vanish. That would be both a momentous discovery and a dire warning about our own future. What killed them? Resource depletion, environmental collapse, nuclear war, artificial intelligence gone wrong, a pandemic. Understanding what happened to a dead civilization might teach us how to avoid the same fate. There's also the question of whether we should announce our presence. Some scientists, including Stephen Hawking, warned against actively transmitting messages to the stars, arguing that advertising our location to potentially hostile aliens could be dangerous. We simply don't know whether extraterrestrial civilizations would be friendly, indifferent, or hostile. History shows that when technologically advanced civilizations encounter less advanced ones, the results are often tragic for the less advanced group. If we're the less advanced civilization in a galactic context, perhaps caution is wise. Others argue that we've already announced our presence through decades of radio and television broadcasts leaking into space. Any civilization within 100 light-years with sensitive enough receivers might already know we're here. Moreover, the benefits of potential contact, shared knowledge, cultural exchange, knowing we're not alone, might outweigh the risks. This debate remains unresolved with passionate advocates on both sides. Imagine the day when humanity receives an unmistakable signal from an intelligent alien civilization. Not something ambiguous that could be a natural phenomenon, but a clearly artificial message, perhaps a sequence of prime numbers, or pi calculated to many decimal places, or encoded images. That day would mark a before and after moment in human history. Everything would change: philosophy, religion, science, culture. All would need to incorporate the reality that we share the universe with other minds. If that civilization is at a star system within reasonable interstellar travel range, sending a mission would immediately become a global priority. Resources that currently seem impossible to mobilize might suddenly become available when the goal is making contact with alien intelligence. The mission would carry not just scientists and equipment, but representatives of humanity, our art, music, literature, history, and messages expressing who we are and what we value. The journey to another star wouldn't be quick, even in the most optimistic scenario. Decades would pass during the voyage, possibly centuries. The crew, whether human, AI, or some combination, would have time to prepare, to study everything we know about the destination, to plan their approach and first observations. The anticipation would be extraordinary. After all that time, all that distance, finally approaching another world that we know harbors intelligence. What would first contact actually look like? Science fiction has explored countless scenarios, from hostile invasions to benevolent exchanges to incomprehensible alienness, where communication proves impossible. The reality would depend entirely on the nature of the civilization we encounter. Are they biological like us, or something entirely different, silicon-based, energy beings, hive minds, machine intelligence? Do they think in ways we can understand, or are their minds so alien that meaningful communication is impossible? One thing seems likely. Any civilization we contact through interstellar travel will be either much less advanced than us, perhaps pre-industrial or early industrial, or much more advanced. The window where two civilizations are at roughly the same technological level is probably very narrow in cosmic terms. Technology advances rapidly once it begins. If we can cross interstellar space to visit them, we're probably the more advanced civilization. If they're broadcasting radio signals we can detect but haven't visited us, they might be roughly comparable. If they've already mastered interstellar travel and are exploring the galaxy, they're far ahead of us. Meeting a less advanced civilization raises profound ethical questions. Do we reveal ourselves? Do we share technology? History provides sobering examples of what happens when technologically advanced cultures encounter isolated groups, often resulting in cultural destruction, even when intentions are benevolent. The prime directive from Star Trek, the rule that forbids interfering with less advanced civilizations, might seem like fiction, but it reflects serious ethical reasoning about contact scenarios. Meeting a more advanced civilization could be humanity's greatest opportunity or greatest danger. If they're benevolent and willing to share knowledge, we might leap forward thousands of years in technology and understanding within a generation. If they're exploitative or hostile, we might face subjugation or extinction. If they're indifferent, we might find ourselves trying desperately to gain attention from beings who regard us the way we regard insects. Interesting in an abstract sense, but not worth serious consideration. Most scientists who think seriously about this suspect that any civilization advanced enough for interstellar travel has probably solved its internal conflicts and resource problems. Societies that remain violent and destructive likely don't survive long enough to develop such advanced technology. Nuclear weapons, climate change, artificial intelligence, bioengineered pandemics. Our own civilization faces multiple existential risks. A civilization that successfully navigated through these filters and emerged capable of crossing interstellar space probably did so by developing wisdom alongside technology. But that's speculation based on limited data, a sample size of one intelligent species ourselves, which hasn't yet demonstrated the ability to solve our own existential challenges. We simply don't know whether intelligence inevitably leads to wisdom, or whether the galaxy is littered with the ruins of civilizations that developed powerful technology but lacked the maturity to use it responsibly. Let's return to Earth and consider what interstellar exploration means for us right now, today, in the early decades of the 21st century. We're not launching generation ships or building laser arrays powerful enough to push nanocrafts to relativistic speeds, not yet. But we're laying groundwork. Every advance in propulsion technology, materials science, robotics, artificial intelligence, and biological life support systems brings interstellar travel incrementally closer to reality. The International Space Station teaches us about long-duration spaceflight. Mars missions planned for the 2030s will teach us about operating autonomous systems on distant worlds with long communication delays. Lunar bases might teach us about building self-sufficient settlements using local resources. Asteroid mining ventures, if they prove economically viable, might establish the space-based infrastructure that eventually makes interstellar missions possible. Young people alive today might live to see the first dedicated interstellar probes launched, perhaps small, fast nanocrafts on flyby missions to Alpha Centauri or Proxima Centauri. Children born in the next few decades might see the first images transmitted back from another star system during their lifetimes. That moment, when humanity first sees close-up pictures of worlds orbiting another sun, will rank among the greatest moments in our species' history. And perhaps if we're fortunate and wise, if we solve our problems rather than succumbing to them, if we continue pushing the boundaries of what's possible, humans, centuries from now, might step onto soil that orbits a star other than our sun. They'll look up at an alien sky with unfamiliar constellations, find our sun reduced to a faint point of light among thousands of others, and know that humanity has truly become a spacefaring civilization. The challenges are immense. The distances are vast, almost beyond comprehension. The energy requirements are staggering. The engineering problems are unprecedented. The timescales are measured in generations or centuries. Yet nothing in physics absolutely forbids interstellar travel. It's extraordinarily difficult but not impossible, and that makes all the difference. Throughout history, humans have accomplished things that seemed impossible to earlier generations. We've split the atom, eradicated diseases, connected the entire world through instant communication, decoded the human genome, and walked on the moon. Each achievement required vision, dedication, resources, and time. Interstellar travel requires all of these on a scale we've never attempted, but that doesn't make it fantasy. The physicist Freeman Dyson once said that there are two kinds of impossible. The first kind is something like traveling faster than light, which violates the laws of physics as we understand them. The second kind is something like traveling to the stars, which is possible in theory but overwhelmingly difficult in practice. Interstellar travel is the second kind of impossible. It doesn't violate any known laws of physics. We know it can be done because we understand the principles involved. What we lack isn't knowledge of the basic physics, but the engineering capability to implement those principles on the required scale. That capability will grow. Every year, materials get stronger and lighter. Propulsion systems become more efficient. Power sources become more compact. Manufacturing becomes more precise. Costs decrease as technologies mature. The impossible of today becomes difficult tomorrow and routine the day after. Not quickly, this is the work of generations, but progress is real. Perhaps most importantly, interstellar exploration expands our perspective in ways that benefit us immediately. When you're working on problems that operate on timescales of decades or centuries, spanning distances of light years, requiring coordination across entire civilizations, your thinking changes. Petty concerns shrink. Long-term planning becomes natural. International cooperation seems obvious. After all, from the perspective of another star, Earth has no borders, no separate nations, just one small world with one species trying to understand its place in the cosmos. The technologies developed for interstellar exploration will have applications here on Earth. Better energy systems could address climate change. Advanced life support and recycling could help manage resources on our own planet. Propulsion research might lead to breakthrough energy technologies. Autonomous AI systems might solve problems we can't. Medical advances necessary for long-duration spaceflight might extend healthy human lifespans. History shows that pushing boundaries in one area creates unexpected benefits in others. So while we might not be traveling to other stars ourselves, while the first interstellar missions might not launch in our lifetimes, the work happening now matters. Every step toward the stars is also a step toward solving problems here at home. Every advance in space technology is an advance in human capability generally. Every moment we spend contemplating the vast universe and our place in it is a moment we spend thinking beyond ourselves. The stars have captivated humans since we first looked up and wondered what those lights in the night sky might be. For most of human history, they remained forever beyond reach, distant and untouchable. Now, for the first time in our species' existence, we can seriously discuss reaching them. Not easily, not soon, but genuinely. With engineering and physics, not magic or wishes, that represents something profound. We stand at a threshold in human history, the moment when we transition from wondering whether interstellar travel is possible to figuring out how to actually do it. The first steps are happening in our lifetime. The foundations are being laid right now. And though the journey will be long and difficult, though most of us won't live to see the destination, we're part of the beginning of humanity's journey to the stars. In the end, perhaps that's what interstellar exploration really represents. Not an escape from Earth or a solution to immediate problems, but an expression of something fundamentally human. We explore because we're curious. We reach beyond our grasp because we imagine what might be possible. We work on problems that won't be solved in our lifetimes because we believe the future matters. We look at the impossible and ask, how might we make this possible? The universe is vast, ancient, and full of wonders we've barely begun to discover. Somewhere out there, orbiting other stars, are worlds we can barely imagine. Some might harbor life, some might harbor intelligence, some might just be barren rocks, but beautiful in their own way. telling stories of formation and evolution written in stone and ice. We won't reach them quickly. The fastest thing we can build still isn't fast enough to make interstellar travel easy. But that's okay. The universe has been here for nearly 14 billion years. The stars will still be there in 1,000 years or 10,000. We have time. What matters is that we start, that we take the first steps, that we commit to the long journey ahead, because ultimately, that's what defines us as a species. Not that we're content with where we are, but that we always look beyond the horizon and ask, what's out there? And then somehow, against all odds, we find a way to go see for ourselves. If this deep dive into the physics, challenges, and sheer audacity of interstellar travel fascinated you, head over to my video called Why the Fastest Thing in the Universe Still Isn't Fast Enough at the left side of the screen. In this video, we break down the cosmic speed limit and explore why even at 300,000 kilometers per second, the universe is still frustratingly vast. See you there.